Okay. Okay, yaar. So, hi everyone. So, good evening all. So, first of all, let me know whether my audio and video are clear or not. So, let me know whether audio and video are clear or not. See, if it is not clear, please let me know through chat box here. Right? Okay. Okay. So, we are dealing with the subject electromagnetics, and in the last session we have started Poynting theorem. Yes or no? Okay. And we have solved some problems based on Poynting theorem. We have seen the concept of Poynting theorem, and also mainly we have studied about the time average Poynting vector, how to determine the time average Poynting vector whenever they have given the electric field and magnetic field as real time solutions, and whenever they have given the electric field and magnetic field in terms of complex solutions. So in that case, how to calculate average Poynting vector. So those things we have seen. Yes or no? And also we have derived the expressions for time average Poynting vector for different cases here. So like for lossless medium, what is the time average Poynting vector, and for lossy medium, how to calculate the time average Poynting vector. So these things we have seen in the previous session, right? Okay. So now today we'll try to solve some more problems based on this Poynting theorem, right? Okay. Okay, yeah. So let's write down the problem. A wave traveling in a lossless non-magnetic medium has electric field has an electric field amplitude of 24.56 volt per meter, and average power density of 2.4 watt per meter square. Then determine the phase velocity. Determine the phase velocity of the wave. Then determine the phase velocity of the wave. Okay. So see here, what is the question they are asking here is a wave traveling in a lossless non-magnetic medium. A wave traveling in a lossless non-magnetic medium has an electric field amplitude of what? That means they have given the amplitude of electric field. So that is 24.56 volt per meter, and average power density of 2.4 watt per meter square. So this wave is having an average power density. Average means time average here, right? So the time average power density of 2.4 watt per meter square. So that means they have given S average, right? Then they are asking determine what? Determine the phase velocity of the wave. Then they are asking to determine the phase velocity of the wave. Okay. Okay here. So see here, what they have given here? They have given the amplitude of the electric field. So let us say the amplitude of electric field, so let us say I am representing with E naught, which is equal to, they have given it as 24.56 volt per meter. And then what they have given? They have given average power density here. They have given the average power density. So that is S average. So what they have given? Average power density, how much they have given? 2.4 watt per meter square. 2.4 watt per meter square. And also they are saying that the medium is what here? Medium is lossless and non-magnetic. They are saying that the medium is lossless and non-magnetic. So what do you mean by lossless medium here? Lossless medium means, what is the condition? We know that if the medium is lossless, then the conductivity of the medium is equal to 0, and epsilon r and mu r values must be what? Must be real quantities. Understood? So then we can say the medium as lossless medium. Conductivity of the medium is equal to 0, mu r and epsilon r values will become real. Right. Next, what do you mean by non-magnetic medium here? So non-magnetic medium means the relative permeability of this medium is equal to what? Is equal to 1. Then we can say that medium as non-magnetic. Right. Okay. So now what they are asking here? They are asking to determine what? Determine the phase velocity. So you have to determine the phase velocity of the wave. So phase velocity of the wave. This is what you have to determine. So what is the phase velocity of the wave here? Tell me. So if anybody has done this problem, please tell me. How you can determine the phase velocity of the wave? See, here they have given the hint for a relative permeability, that is non-magnetic medium, which means mu r equal to 1, right? And they have given that lossless medium, which means sigma is equal to 0. Epsilon r and mu r values are real. So in this medium there will be no attenuation constant, right? So alpha will also become what? Alpha will also become 0, right? So these things we can determine, right? So now if you want to determine the phase velocity in a lossless non-magnetic medium, what is the expression for phase velocity here? So phase velocity is equal to, I can write this as what? Phase velocity is equal to what here? See, we know that omega by beta here, omega by beta is equal to what? Is equal to phase velocity, right? Okay. Okay. So right. So where beta is equal to what? Beta is equal to omega into what? For a lossless medium, beta is equal to what? Omega into square root of mu epsilon, which is equal to what? Omega into square root of mu naught epsilon naught mu r epsilon r, right? Okay. So this I can write it as omega by c into square root of mu r epsilon r. Yes or no? Okay. So square root of mu naught epsilon naught is nothing but what? 1 by c. So you are having square root of mu r epsilon r, here omega. So in this manner I can write beta equal to omega by c into square root of mu r epsilon r. So therefore phase velocity will become equal to what? Phase velocity I can write it as simply c by what? C by square root of mu r epsilon r. Yes or no? If you substitute in place of beta, if you substitute omega by c into square root of mu r epsilon r, what you are going to get? The phase velocity is equal to c by square root of mu r epsilon r. So here they have given mu r value, so that is non-magnetic medium, that is mu r value is equal to 1, but they have not given value of epsilon r. Understood? See, in the problem, if they have not given any clue to determine the relative permittivity, only in that case we will consider the relative permittivity equal to 1. But here in this problem they have given what? They have given the power density. Yes or no? They have given the power density, right? So they are asking to determine phase velocity. So here they have given the power density S average is equal to what? S average is equal to 2.4 watt per meter square. Yes or no? So this is the average power density they have given. And in a lossless medium, In a lossless medium, we know that the average power density is equal to what? Half into E naught square divided by eta, where eta is the intrinsic impedance for the lossless medium, right? So half into E naught square by eta. So this is equal to what? This is equal to, they have given 2.4 watt per meter square. Okay, so now from here they have given the amplitude of the electric field also. What is the amplitude of electric field they have given? They have given it as 24.56 volt per meter. So substitute this value and try to determine eta here. Why we have to determine eta means, see, if you determine eta value, so eta is equal to what? For lossless medium, eta is equal to, we know that it is equivalent to eta naught into square root of mu r by epsilon r, where eta naught is nothing but intrinsic impedance for free space. So we know this value, so that is 120 pi ohm. Mu r value they have given that it is 1, right? So from here you can determine what? You can determine epsilon r value. Yes or no here? So once you determine epsilon r value, then you can easily determine the phase velocity, right? So just to do that one here, just to do that one. So what you have to do? First you have to determine eta value. So from eta value you can determine epsilon r value. So if you know epsilon r value, then you can determine phase velocity. That's it. Okay. Okay. So from here what you are going to get? You are going to get eta is equal to 24.56 whole square divided by what? Divided by 2 into 2.4. Okay, so do this here. What you are going to get? Tell me. So do this and what you are going to get? Tell me. 24.56 square divided by 2 into 2.4. Okay, so you are going to get approximately 125.67 ohms. 125.67 ohms. So this is what you are going to get intrinsic impedance value, right? Okay. So once you got intrinsic impedance value, now you can easily determine epsilon r value, right? So eta is equal to eta naught into square root of mu r by epsilon r. Mu r value is 1, eta value is 125.67, which is equal to what? Eta naught value, that is 120 pi divided by what? Divided by root epsilon r. So divided by root epsilon r, right? Okay. So from this here, from this epsilon r is equal to what? Is equal to 120 pi divided by 125.67 whole square, right? Okay. So let me know if there is any calculation mistake, please let me know here, right? So 120 pi divided by 125.67, you are going to get approximately 3. So this value we are getting approximately 3 here. Okay, so that means 3 square is 9. So approximate value 120 pi divided by 125.67, we are getting 2.9999 something. So that means we can approximate it as equal to 3. So therefore epsilon r value is equal to what? Is equal to 9. So once we know epsilon r value, then we can determine what? Phase velocity. Yes or no? Okay. So what is phase velocity here? Tell me. So phase velocity is equal to what? Is equal to C by square root of mu r epsilon r for lossless medium. Yes or no? So this mu r value is 1. Just now we have determined epsilon r value, that is 9, and this C value is 3 into 10 to the power of 8 meters per second. So substitute all this. What you are going to get? Here 3 into 10 power 8 divided by square root of 9 is nothing but 3. So 3 will get cancelled. You are going to get what? Phase velocity is 1 into 10 to the power of 8 meters per second. Okay. So this is the phase velocity of the wave. This is the phase velocity of the wave in the given lossless non-magnetic medium, right? Okay. Okay. So this is very simple question here. I think you can easily solve this question. So just where the students will do mistake is generally, if they don't determine this epsilon r value and directly try to determine phase velocity as equivalent to c, if you write just simply phase velocity is equivalent to c by considering mu r epsilon r values as 1, okay, then you are going to get wrong answer. Mu r value anyway they have given that non-magnetic medium, so that's why you have to consider mu r value 1, but you don't know epsilon r value. See, if they have not given in the problem, if they have not mentioned anything here, any clue they have not given in order to determine epsilon r value, only in that case you have to determine epsilon, you have to consider epsilon r value as 1. Understood? So here they have given S average. So from that you can determine intrinsic impedance value. So from that intrinsic impedance value you can determine the epsilon r value. So once you determine epsilon r value, then you can easily determine the phase velocity. Understood? Okay. So don't simply take every time mu r equal to 1, epsilon r equal to 1. It all depends upon the given problem here. Right. So if there is no clue and simply they are saying that the medium is lossless, something like that, and if they have not given any clue to determine the relative permeability or relative permittivity, only in that case you have to assume them as 1. Right? Okay. 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 So next problem, write down next problem. Write down here. So second problem. The electric field phasor, the electric field phasor of an uniform plane wave, traveling downward in water, is given by E bar is equal to 5 into e power minus 0.2 z into e power minus j 0.2 z ax cap volt per meter, okay. So where az cap is the downward direction, and z equal to 0 is the water surface. If conductivity sigma is equal to 4 7 per meter, then obtain the expression, for the average power density, right. Okay. So let us see what is the question they are asking here is the electric field phasor. See, already I have told what do you mean by the electric field phasor here. So phasor form means they will give only the spatial variations here. So if they have given only spatial variation, you have to understand that it is phasor form. See, actually whenever we are saying the electric field and magnetic field of an electromagnetic wave means the electric field and magnetic field, we know that these two fields are must be what? Must be functions of both space as well as what? The electric field and magnetic field must be functions of both space as well as what? As well as time. And also we know that this electric field and magnetic field are time harmonic fields. So which means they are going to vary sinusoidally with respect to time. So this one I can write it as E bar of S into what? Into e power j omega t. So this one I can write it as spatial variation multiplied by e power j omega t. So we'll represent the time variation as e power j omega t, which represents that electric field and magnetic field are time harmonic fields because they are varying sinusoidally. They are varying sinusoidally with respect to time. Understood? Okay. So here this is spatial variation. If you represent only spatial variation, then you have to understand that this is phasor form. This is phasor form. See, just by removing e power j omega t term, if you represent the electric field and magnetic field, then it is called as phasor form. Okay. So don't misunderstand that here they have given the electric field only spatial variation, but the electric field must be a function of space and time. Okay, so you should not get those type of doubts because they have given phasor form means they have given only the spatial variation. Understood? Okay. Okay. Right. Okay. Okay. So now they have given the phasor form like this. Now what they are asking here? What they are asking? So uniform plane wave traveling downward in water is given by E bar is equal to, this is the expression, this is the phasor form of electric field they have given. So 5 into e power minus 0.2 z. So that means here the amplitude is decaying exponentially. So which means the medium is lossy medium. That's what you have to understand. Next they have given e power minus j 0.2 z. So this is the spatial phase. This is the phase of the wave. Yes or no? Okay. So they have given it as e power minus j 0.2 z. So it is just like what? E power minus j beta z. Right? Okay. Where az cap is the downward direction and z equal to 0 is the water surface. If sigma equal to 4 Siemens per meter, then obtain the expression for the average power density. So this is what they are asking. Ajay Kumar, hello dear. Good evening dear. Good evening. Right? Okay. Okay, yaar. See here. See, whenever they ask the question like this, they are asking average power density. So what you will do is average power density S average is equal to, you know the formula. So what you will do? Half into. So the medium is lossy medium. The medium is what? The medium is lossy medium. So we know that for lossy medium, the average Poynting vector S average is equal to what? S average is equal to half into E naught square divided by magnitude of eta lossy into e power minus 2 alpha z into cos phi. Here the wave is propagating in downward direction. Yes or no? So they have given z equal to 0 as the water surface and the wave is propagating inside the water in z direction. So they are saying that consider this as what? This as z direction. Understood? So which means the wave is propagating in z direction. Understood? Okay. Okay. So if the wave is propagating in z direction means what is the direction of average Poynting vector? The time average Poynting vector will always points along the direction of wave propagation. So which means it is propagating in az cap. Right? Okay, fine. So now see here. Okay, you have written the formula. Now what you have to determine? You have to determine the amplitude of the electric field. So in the problem, let us check. They have given the amplitude of the electric field. The amplitude of the electric field is E naught value. Sorry, wait. Okay. So they have given here E naught value, the peak amplitude of the electric field, that is E naught. So E naught value they have given. Right, and here e power minus 0.2 z they have given. So that means this is a wait here. Okay, so here they have given E naught value, here they have given e power minus 0.2 z, so which means they have given here alpha value also, yes or no? So this 0.2 represents what? This 0.2 represents alpha value, right? Okay, so we know alpha value and we know the peak amplitude of the electric field, right? Okay, next what you have to determine? You have to determine eta lossy, the magnitude of eta lossy, and you have to determine this phase shift phi. Understood? So this is the time phase shift, yes or no? Remember that this is the time phase shift here. This is the time phase shift between what? Between E and H fields. E and H fields. Yes or no? This phi is nothing but the time phase shift between E and H fields. Remember that. Okay. So now if you just determine this intrinsic impedance here, if you determine the intrinsic impedance for lossy medium, so that is eta lossy is equal to what? Is equal to magnitude of eta lossy at an angle what? It is at the angle is phi lossy. Understood? So actually this angle is nothing but phi lossy here. So if you want, you can represent like this. Right. So you have to determine the magnitude of eta and also you have to determine phi. Right. Okay, yeah. So now first of all, in order to determine these things, you have to know the nature of the medium. Yes or no? So whether the medium is a low lossy, we know just it is lossy, right? But we have to know whether it is low lossy medium or it is a high lossy, low lossy dielectric, or high lossy dielectric, or it is neither low lossy dielectric nor high lossy dielectric, or you can say low lossy dielectric. High lossy dielectric means what? You can call it as good conducting medium. Low lossy dielectric means you can call it as good dielectric medium. So neither low lossy nor high lossy means you can consider it as neither good dielectric medium nor what? Nor good conducting medium. So if you determine the nature of the medium here, then we can write the formula for eta, and thus we can determine the magnitude as well as what? As well as phi. Understood? Okay. So in order to determine the nature of the medium, what you have to determine here? So they have given the conductivity of the medium. Yes or no? So in order to determine the nature of the medium, what you have to determine? Tell what you have to determine. You have to determine sigma by omega epsilon ratio. Yes or no? In order to tell the nature of the medium, you have to determine sigma by omega epsilon ratio. In the problem, what they have given? They have given sigma value, right? They have given sigma value, and here if you observe, they have not mentioned anything about what? Anything about omega, right? So here, if you try to determine sigma by omega epsilon ratio, then here you know only sigma value. Understood? So you don't know, they have not given omega value, right? So if they have not given omega value, how you can determine this one? It is not possible now, right? So here what you have to do here is if you just observe the expression here, the given expression for electric field, so you can conclude one thing. So what is that here? If you are getting any idea, please let me know. If you are getting any idea just by seeing the expression for electric field. Just by seeing this expression for electric field, what is the idea you are going to get? See, from this expression itself, we can say the nature of the medium. How we can say the nature of the medium? Tell me. See here, this is nothing but what? Here they have given alpha value, right? And here they have given what? Here 0.2. This is nothing but what? This is nothing but beta value. So that means here they have given alpha is equal to what? Alpha is equal to 0.2, and beta is also equal to what? Beta is also equal to 0.2. So alpha equal to 0.2 Nepper per meter, beta is equal to 0.2 radian per meter. Okay, so from the values of alpha and beta, what we can guess here? What we can guess? So we can guess that the medium is what? Good conducting medium, because we know that in a good conducting medium, the expression for in a good conducting medium here, in a good conducting medium are high lossy dielectric. What is the expression for alpha? The expression for alpha and the expression for beta both are same. Yes or no? We know that alpha is equal to square root of omega mu sigma by 2 Nepper per meter, and also beta is also equal to square root of omega mu sigma by 2 radian per meter. Understood? So since the expressions for alpha and beta are same in case of good conducting medium. Understood? Okay, so we can say that since here alpha value is same as what? Is same as beta value. So that's why we can confirm that it is what? It is a good conducting medium. So from the given expression itself, see, they will give the clue in some way or the other here. So you must be in a situation to identify that one. So you have to catch up that clue. Understood? So once you have done that one, so then the problem will be very much simple. Right? Okay, so they are not going to give you the problems which are having huge calculations like that in GATE exam, right? So they will give you the problems which is having less mathematical calculations in general, right? But you have to apply the concept. So just if you get that logic and if you get that concept, then the problem solving is very simple here, right? Okay, in general, in case of EMT I am saying, right? Okay. Right. So we have concluded good conducting medium. So if you want here, if you are not getting this idea, let us assume you are not getting this idea. So but here you have confirmed that we know that this is alpha value and this is beta value, right? Okay. Right. Okay. So there is no other way here. You have to follow this one only. There is no other way. Right? Okay. So here this value is alpha and this is beta. So alpha value will be same as beta value only in case of good conducting medium. So that's what you have to identify from this. Right? So once you have identified that this medium is a good conducting medium, then you can happily determine what you have to determine here. You have to determine the magnitude of eta lossy and you have to determine this phi lossy, or simply phi. You can say simply phi. Understood? So you have to determine the magnitude of eta and also you have to determine the phi. Right. So now since we have identified that medium as good conducting medium, so I am writing here for good conducting medium here. For good conducting medium, what is the expression for intrinsic impedance here? So the intrinsic impedance for a good conducting medium is equal to what? Is equal to square root of what? Square root of j omega mu divided by sigma. Right. See, we know in general for a lossy medium, the intrinsic impedance is square root of j omega mu divided by what? Sigma plus j omega epsilon. So in a good conducting medium, this sigma value will be very much larger than this omega epsilon value. Yes or no? So that means you can neglect this term here. You can neglect this term when compared to what? When compared to sigma in case of good conducting medium. So if you neglect this term, when compared to sigma, then you are going to get the expression as what? For good conducting medium, you are going to get the expression as square root of j omega mu by sigma. Right? Okay. Okay. So this is the expression for the good conducting medium. Right? So this is equivalent to what? This is equivalent to, I can write it as, so what is the magnitude here? Magnitude is nothing but square root of omega mu divided by sigma. And what is the phase shift? So phase shift, J is nothing but 90 degrees. J means phase shift is 90 degrees. So it is under root. So if you take that 90 degrees out of the root, you can write it as what? You can write it as at an angle 45 degrees. Right? Okay. Okay. So eta for good conducting medium. So the magnitude is equal to square root of omega mu divided by sigma, and the phase shift for good conducting medium is equal to what? It is equal to 45 degrees. Always remember here, in an good conducting medium, the electric field leads magnetic field by how many degrees here? 45 degrees. See here, eta means what? It is nothing but the ratio of E to H. So the electric field will always leads H field by 45 degrees in case of good conducting medium. This is a standard result here. So if the medium is good conducting medium, electric field will always leads magnetic field by 45 degrees, right? Okay, so here we got phi value. So phi value is nothing but 45 degrees. So here what is the magnitude here? Magnitude is equal to square root of omega mu by sigma. So again here we are getting the omega value. Yes or no? Again here we are getting the omega. Understood? But here they have not given omega value. So in this problem they have not mentioned anything about the omega. So how you can calculate this magnitude of intrinsic impedance? How you can calculate here? In the problem they have not given omega value, right? Okay, so how you can calculate the magnitude? How you can calculate the magnitude? Right? Okay, yeah. So for that, what I am going to do here is see, so eta for good conducting medium magnitude is equal to square root of omega mu divided by what? Divided by sigma, right? Okay. Okay, yeah. So now what I am doing here is I am multiplying with sigma and dividing with sigma. So then I am going to get what? Square root of omega mu sigma divided by sigma square. Okay. Okay, yeah. So square root of omega mu sigma by sigma square. So in good conducting medium here, in a good conducting medium, what is the skin depth here? What is the skin depth in case of good conducting medium? Is equal to what? Is equal to 1 by square root of pi f mu sigma. Yes or no? Okay. So 1 by square root of pi f mu sigma. Right. So now I can write this as, so here I can write it as 2 pi f mu sigma divided by sigma square. Right. So this I can write it as root 2 divided by sigma into what? Into square root of pi of mu sigma is nothing but what? Square root of pi of mu sigma is nothing but what? Is nothing but 1 by delta. So I can write it as 1 by delta for good conducting medium. 1 by delta. So therefore the magnitude of good conducting medium intrinsic impedance, okay, is equal to what? Is equal to, I can write it as root 2 by sigma into delta for good conducting medium. See, what is 1 by delta here? What is 1 by delta? We know that always delta is equal to what? Skin depth is equal to what? 1 by alpha. Yes or no? Okay. So 1 by delta means you can write it as what? Root 2 by sigma into what? Into alpha. So alpha for good conducting medium. Right. So finally we got the expression for intrinsic impedance in case of good conducting medium as what? Root 2 by sigma into alpha. Now here they have given sigma value, they have given alpha value also. So just substitute these values in order to get the magnitude of intrinsic impedance. Right. Okay. So what you are going to get, tell me. So this is equivalent to root 2 divided by sigma value they have given 4 and alpha value is 0.4, I think, right? So alpha value is 0.2, alpha value is 0.2, right? Okay. So alpha value is 0.2. So root 2 by 4 into 0.2. Okay. So what you are going to get? What you are going to get, tell me. So root 2 into 0.2 divided by 4. So you are going to get 0.0707 ohms. 0.0707 ohms. right? So this is the magnitude. Okay, so now determine here. So in case of good conducting medium, so now we have determined the nature of the medium, that is good conducting medium. So in this case, S average is equal to what? I can write it as half into E naught square divided by magnitude of what? Magnitude of intrinsic impedance of good conducting medium into what? E power minus 2 alpha z into cos phi. So this phi is for good conducting medium, and the wave is propagating in AZ cap direction. So the units are nothing but watt per meter square, right? Now just substitute all the values here. We know that alpha is 0.2, alpha is 0.2, and then this value eta just now we have determined magnitude of eta 0.0707. So this value is 0.0707, and this phi value, so this phi value they have given we have determined it as 45 degrees, right? And this E naught, so E naught value is how much here? E naught value is 5, right? Right, E naught value is 5. So E naught value is 5. So substitute all this here. So you are going to get 25 by 2 into 0.0707 into e power minus 2 into 0.2 into z into cos 45 degrees AZ cap watt per meter square. Okay, so they are asking the expression for average power density here. So this is the expression you are going to get, right? Okay, so if you want, you can simplify this further. So what you are going to get? So 25 divided by 2 into 0.0707 is 176.803 into e power minus 0.4 z. So cos 45 is root 2. Okay, so AZ cap watt per meter square. So you can simplify this value further here. So divided by root 2. So 125, you will get 125 here. So this value you will get 125. Approximately 125 you will get. Okay, so this is the expression for what? This is the expression for average power density. Average power density of the wave that is propagating inside the water. Understood? Okay, now you can determine the average power density value at any location z. At any location z, you can determine the average power density value, right? So this is the expression here. Yes, here, that's what I have written, Selvaraj. Okay, okay. So I hope this problem is clear, right? Right. So write down next problem here. Write down next problem. Right. Okay. So write down next problem here. So third problem. In a region E and H fields are given as, in a region E and H fields are given as E bar is equal to 100 into J AX cap plus 2 AY cap minus J AZ cap into e power j omega t, and H bar is equal to minus AX cap plus J ay cap plus az cap into e power j omega t. Then find the average power flow density and direction of power flow in the region. Okay. So what is the problem they have given? So they are saying that in a region the electric and magnetic fields are given as E bar is equal to 100 into J AX cap plus 2 into AY cap minus J into AZ cap multiplied by e power J omega t. Understood? So here if you observe the amplitude of the electric field, here the amplitude of the electric field is a complex quantity. Understood? Okay. And the field is time harmonic, so that's why they are represented with e power j omega t. And H field, so H field is equal to minus AX cap plus j AY cap plus AZ cap into e power j omega t. So here also they have given the amplitude of the H field is a complex quantity. So here the amplitude of electric field and the amplitude of H field both are what? Both are complex quantities. Right, this is what they have given. So in this case they are asking to determine the average power flow density. So which means they are asking to determine what? To determine S average. Right, and also they are asking to determine what? To determine the direction of power flow in that region. So they are asking to determine the direction of power flow in that region. So these two things they are asking here. So one is they are asking the average power flow density, that is nothing but the time average Poynting vector, and also they are asking the direction of this power flow in that region. Right, so they are also asking the direction of the power flow. So these two things they are asking here. So how you can determine? Tell me. How you can determine? Tell me. How to determine here? See, already I have told here, whenever they have given the electric field and magnetic field, the electric field and magnetic field amplitudes, if they have given in complex form, if they have given the electric field and magnetic field in complex form, then in that case how to determine the average power flow density, that is S average, right? So that is half into real part of E bar cross H bar conjugate, right? Okay, here. So I am just copying these expressions here. Right, okay. So whenever E bar and H bar are complex quantities, so whenever E bar and H bar they have given as complex, right, then in that case what I have told, the average Poynting vector you have to determine by using this formula, that is half into real part of what? E bar cross H bar conjugate. So what do you mean by H bar conjugate here? Wherever you are having J, there you have to replace with minus J, right? Okay, so here I am writing the expression for H bar conjugate. So H bar conjugate is equal to what? Minus AX cap, and here you are having J. So wherever you are having J, just replace with minus. Okay, so minus J AY cap plus what? Plus AZ cap multiplied by, here you are having e power j omega t, so h conjugate means you have to replace with minus j, so you are going to get e power minus j omega t, right? Okay, so now just try to determine this e bar cross h bar conjugate, e bar cross h bar conjugate. So what is e bar cross h bar conjugate here, tell me? So e bar cross h bar conjugate is equal to, so I am taking this 100 outside here, right? Okay, so I am determining the determinant, I am writing in determinant form. So this is ax cap, ay cap, az cap. So here you are having j, and here you are having 2, and here you are having minus j, and for a h conjugate you have to write the expression for h conjugate. So h conjugate, here you are having minus 1, and here minus j, and here you are having plus 1, right? And if you multiply e power j omega t, if you multiply e power j omega t with e power minus j omega t, you are going to get 1, you are going to get 1. Okay, so finally e bar cross h bar conjugate is equal to 100 into, so you can write it in this determinant form. So if you expand this one, you are going to get this value, right? Okay, so tell me what you are getting here, what you are getting, e bar cross h bar conjugate, tell me. So 100 into, so ax cap, so ax cap into 2 minus of minus into minus will become plus j square, so j square means minus 1, so you are going to get minus 1 here, right? So this is ax cap component. Next, minus ay cap, so what you are going to get, ay cap, j here, right? So minus j minus of minus into minus will become plus 1 into j is j, right? Next, plus az cap into j square is minus 1, here you are having minus, so minus of minus will become plus, so 1 minus so minus 1 into 2 is minus 2, right? Okay, so this y component will become what? This y component will become 0. So therefore what you are going to have, 100 into 2 plus 1, that is 3 ax cap plus what? Plus 3 az cap. So this is the e bar cross what? E bar cross h bar conjugate. So anyway we got e bar cross h bar conjugate as real quantity. So the real part of this one is the same thing. Yes or no? Okay. So therefore S average is equal to what? Is equal to half into real part of e bar cross h bar conjugate is equal to what? Is equal to half into 100 into 3 ax cap plus 3 az cap. Okay, so 2 ones, 2 50s, so you are going to get 150 ax cap plus what? Plus 150 az cap, or you can take 150 common, so 150 into ax cap plus az cap watt per meter square. Okay, so this is the time average Poynting vector we got, so that is 150 ax cap plus az cap watt per meter square. Now tell me, they are also asking to determine the direction of the power flow, yes or no? So the direction of the power flow they are asking. So here we have determined the power flow density, so that is S average value. So this is the S average value, fine. This is the S average value we have determined, fine. So now they are asking the direction of power flow, the direction of power flow. What is the direction of power flow here? Tell me, what is the direction of power flow? We know that the time average Poynting vector will always points along the direction of what? Along the direction of wave propagation, yes or no? Okay, so the power flow will be always along the direction of wave propagation, right? So now tell me, what is the direction of power flow in this case? What is the direction of power flow in this case? Tell me. Tell me here. Tell me, Selvaraj. What is the direction of power flow? 45 degrees on the ZX plane. Okay. So see here how we can say the direction of power flow. See here, what is the magnitude here? What is the magnitude of S average? Tell me. What is the magnitude of this pointing vector? Tell me. And the power flow direction here, the direction of power flow, direction of power flow is nothing but what? Is nothing but direction of what? Direction of S average, isn't it? Okay. So direction of power flow is nothing but what? Direction of S average. So what is the magnitude of S average here? What is the magnitude of S average? Tell me. What is the magnitude of S average? What is the magnitude of S average? 5 root 6. 5 root 6. Is it 5 root 6 magnitude? Please check Selvaraj. We got S average is equal to 150 into AX cap plus AY cap. Okay. See, this is very simple here. So everybody will solve up to this here. So here whenever they are asking the magnitude, if they ask magnitude separately and direction separately, so here most of the persons will do mistake, right? Tell me what is the magnitude? It is not 5 root 6 here, it is not 5 root 6. See here. So generally whenever they get the answer like this here, so what the students will do is, in hurry they will say the magnitude of S average, they will say it as 150, and the direction they will say simply AX cap plus AY cap. They will AX cap plus, sorry, this is AZ cap now, AX cap plus AZ cap. We got AX cap plus AZ cap. AX cap plus AZ cap, right? So they will say simply direction as a AX cap plus AZ cap and magnitude as 150. Okay, so this is absolutely what? This is absolutely wrong. So generally in the examination here, in a hurry, so what they will do is whenever they get the answer, okay, so what, just by seeing that they will say simply 150 as magnitude and AX cap plus AZ cap as a direction, which is absolutely wrong. See here, see what is the magnitude of this vector here? S average is equal to 150 into AX cap plus what? Plus AZ cap. So what is its magnitude? So the magnitude is nothing but what? The magnitude is nothing but square root of 150 square plus what? 150 square. So which is equal to what? 150 root 2. So the magnitude is 150 root 2. And the direction. See, remember the direction will always given by what? Given by unit vector. Whenever they are asking the direction here, you have to determine the unit vector. So so unit vector will always gives the direction, So if you want to determine the unit vector, if you want to determine the direction, then you have to determine the unit vector along what? Along S average. So what is the unit vector here? What is the unit vector along S average? Is equal to what? Is equal to, so how to determine? Take the vector and divided by its magnitude. So what you are going to get? So 150 into AX cap plus AZ cap. So this is the vector divided by its magnitude. What is its magnitude? 150 root 2. Okay. So here 150 will get cancelled. So therefore the time average pointing vector, the direction of power flow is equivalent to what? Is equivalent to AX cap plus AZ cap divided by what? Divided by root 2. Okay. So this is what you have to tell. So whatever Selvaraj has told, that is in ZX plane. So he has told that this is Z axis and this is X axis, right? So Here the unit vector a cap s average is pointing in this direction. Understood? So its x component is what? Its x component is a by root 2. Yes or no? Its x component is 1 by root 2 and its its z component is 1 by root 2 and its x component is also what? 1 by root 2. So this angle theta is equal to what? Theta is equal to 45 degrees. So this is what he has told here. So the direction is, he has told that in zx plane it is going to make some 45 degrees like that. So this is also correct. This is also correct. Understood? Okay. Okay. Yes. Right. Okay. So generally you have to give the answer in this manner. Just determine the unit vector that is going to give you the direction. Okay. Okay. Right. Okay. So next, write down next problem. So next is, I have taken gate problem here, a gate problem. Okay. So write down the problem. The electric field of an uniform plane wave traveling in free space. Traveling in free space. So free space means it is lossless medium here, right? So traveling in free space is given by the following expression. So they have given it as E bar of x comma t is equal to 24 pi into cos of omega t minus beta x ay cap volt per meter. See, in general, whenever they have given the problem, so this phase constant they will represent either with beta or they will represent with kr, right? Okay. So don't confuse between those two, both are same, right? So in this field consider a square area. Of 10 centimeter into 10 centimeter on a plane x plus y equal to 1. Then the total time average power in milliwatts passing through the square area is okay. Okay. So this is what they are asking. So what they have given, the electric field of an uniform plane wave traveling in free space. So free space means it is lossless medium here, right? So is given by the following expression. So they have given the expression for the electric field of an uniform plane wave. So that is E bar of x comma t is equal to 24 pi into cos of omega t minus beta x ay cap volt per meter. So this is the amplitude of the wave, and by seeing this you have to identify that the wave is propagating in which direction? Positive x direction, and the electric field is pointing in which direction? The electric field is pointing in y direction, and the wave is propagating in positive x direction. So this is what we can conclude. Next, what they are saying here is in this field, consider a square area of 10 centimeters into 10 centimeters on a plane x plus y is equal to 1. So they have given the equation of a plane here, that is x plus y is equal to 1. So on this plane they are saying that consider a square area having an area of what? 10 centimeters into 10 centimeters, that is 100 centimeter square. Okay, so then they are asking that the total time average power in milliwatts passing through what? Passing through this square area is. So now they are asking what is the total time average power? What is the average power that is flowing through the surface? That is flowing through the surface or passing through the surface or passing through the square area. Understood? So they have given the plane equation, so that is x plus y is equal to 1. So on that plane they are saying that what is the power that is flowing through the surface area or through a square area having an area of 100 centimeter square. So this is what they are asking. Okay. So now see here. So first let us take all the data whatever they have given in the problem. So they have given E bar. So first of all you have to analyze here. You have to analyze what they have given and what they are asking. So once you understand the problem clearly, then you can easily answer the question, right? So this is the electric field they have given. So next what they have given? So they have given the equation of a plane. They have given equation of a plane. Equation of plane or some surface. So they have given it as x plus y is equal to 1. So on this plane they are saying that consider a square area. On this plane they are saying that consider a square area of 100 centimeter square. So that means here they have given the magnitude of what? The magnitude of this square area. So generally the surface area is a vector quantity. Yes or no? So here they have given simply the magnitude of what? The magnitude of that surface area. So that surface area they are considering as square. So that square area they have given it as what? Magnitude of A bar. The magnitude they have given, that is magnitude of A bar is equal to 100 centimeter square. Right. Next what they have given here? That's it now. That's it. Right. And the medium they are saying the medium as free space. Right. Okay, so that means lossless medium. This is lossless medium. Okay, fine. So now see here. So they have given some surface and they are asking the power flow through that surface. The power flow through that surface. See here, if you are having any surface here, let us consider some surface here. I am considering some surface. So let us say this is some surface. Okay, now this is surface area A bar. Let us say this is A bar, right? And the direction of this area is always given by what? Is always given by the unit normal drawn to this surface, right? So if I draw an unit normal to this surface, it is going to point in this direction. So this one I am representing with AN cap. So here A bar is equal to what? A bar is equal to magnitude of A bar and its direction is what? Its direction is along AN cap. Right. So the direction of any surface is given by the unit normal drawn to that surface. So I can represent this A bar as what? Magnitude of A bar into AN cap, where AN cap is the unit normal drawn to that surface. Right. Okay. So now see here. See, I am not talking about the problem here, just I am explaining. Right. Okay. So this is the surface area I have considered. Right. So now let us assume the electromagnetic wave is propagating in this direction. The electromagnetic wave is propagating in this direction. Let us assume. Right. So if the wave is propagating in this direction means the pointing vector or the power flow density is also going to point in the same direction. Yes or no? So let us say this direction is S average. Let us say this is the S average. That is the power is flowing in this direction. So this is I have represented here some vector field. This represents the average power density. Let us assume the average power density. Understood? Okay. So this is the S average, that is the power density that is flowing in this direction, and this is the surface area, right? Okay. So now if I want to determine how much of the power that is flowing through this surface. How much of the power that is flowing through this surface. So in order to determine that, what I will do here is I am going to consider a small differential area on this surface here. I am going to consider a small differential area on this surface. So dA, and its direction is what? Its direction is along AN cap. So I have considered a small differential area on this surface. So what is the power that is going to flow through this small differential area here? So this is the power that is flowing per unit area. Yes or no? S average power density means its units are nothing but what? Watt per meter square. So that means it is going to give you the power that is the power per unit area, the power flowing through this surface per unit area. Now I want to determine the power flow through this small differential area. Then how I can determine here the power flowing through this small differential area? What I have to do? So you have to do the dot product between S average dot what? Dot dA bar. Right? Okay. So dA into AN cap is nothing but what? I can represent simply with dA bar. So this is going to give you the power that is flowing through what? Through this small differential area dA bar. Yes or no here? Okay. Okay. So now if I want the total power flow, if I want the total time average power flow through this total surface, what you have to do? You have to integrate. Right. So the differential area means you are going to integrate with respect to two differential variables. So if you want to determine the power flow through this total surface area means you have to integrate throughout what? Throughout this surface. Right. So this is going to give you what? This is going to give you the power flow through a given surface. This is going to give you the power flow through a given surface. Yes or no? Okay. Okay. See, it is not compulsory that S average has to point in this direction. So S average may point like this also. S average may point like this also. So if it is pointing like this here, so then what will happen? You can resolve this S average into two components. One is what? One is normal to the surface, and another one is what? Parallel to the surface. Understood? So if you observe, only the component that is normal to the surface is going to contribute for the power flow through the surface. So the tangential component or parallel component is not going to contribute for the power flow through the surface. Only these components are penetrating through this surface. Yes or no? So these components, the parallel components, are not penetrating through the surface. Only the components that are normal to the surface are penetrating through the surface. So that means the power flow through a given surface is given by what? Is contributed by what? Is contributed by only the components that are normal to what? Normal to the surface. Understood? So if you want, you can write here, if you want S average that is pointing along the direction of, that is normal to what? The components that are normal to what? Normal to the surface will only contribute what? Will only contribute for the power flow through the surface. See here, see, this differential area is pointing in which direction here? It is pointing in AN cap direction. Understood? Suppose this average here, this S average is having two components here. Let us assume one is parallel component, another one is normal component. So this is pointing in AN cap direction, right? And this is pointing parallel to the surface. So parallel to the surface or tangential to the surface. So I am representing this with a tangential cap. Understood? So whenever you are doing the dot product here, this is nothing but it is having the tangential component, let us say, and also it is having normal component. Okay. So whenever you are doing the dot product, what you are going to get? This is tangential component and here normal component. If you do the dot product between these two, what you are going to get? 0. Yes or no? So that means these components, the components that are parallel to the surface, are not going to contribute for what? Are not going to contribute for the power flow through the surface. Only the components that are normal to the surface are going to contribute for the power flow through the surface. Yes or no? So in general, if you want to determine the power flow through a given surface, so this is the expression. right? Now if suppose instead of giving a open surface here, so this is I have considered here I have considered simply a open surface like this. Okay, if suppose they have given some closed surface, let us say I have considered some closed surface. So in this case how to determine the power flow through this closed surface? Okay, so let us say the power is flowing or leaving, the power is leaving through this closed surface. So in this case, how you have to represent the power flow through this closed surface? So it is very simple here. Since it is open surface, you have done open surface integration. So if you want to determine the power flow through the closed surface, then what you have to do? You have to do closed surface integral S average dot what? Dot dA bar. So this is going to give you the power flow through the closed surface. Understood? So this is just you have to integrate throughout what? Throughout the closed surface. Here you have to integrate throughout this open surface. That is the only difference. That's it. Okay. Okay. Okay, so whether this is this one or this one, both the cases the concept is same. So just the mathematical representation is different, right? So here you are integrating through the open surface, here you have to integrate through the closed surface. That is the only difference, right? Okay. 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 So Selvaraj, you have given the answer. Okay, fine. Here answer is correct, fine, right? But here I want to explain these concepts here, right? Okay, so that's why I have taken this problem, right? So okay, so in our problem they are asking to determine the power flow through the square area. Understood? So that means power flow, average power flow here, yes or no? Average power flow through what? Power flow through the given square area. So how you can represent? Is equal to what? Is equal to double integral S average dot what? Dot dA bar, S average dot dA bar. Understood? Okay. Okay. Yeah. So now see here. So first we try to determine S average here. So the average pointing vector, S average pointing vector. So this is, let us say this is equation 1. So let us name it as 1 here. Okay, so S average is equal to what? Is equal to half into E naught square divided by what? Divided by eta naught. Since the medium is free space, so you can simply write half into E naught square by eta naught. And here they have given the expression for electric field. So here the wave is propagating in which direction? Positive x direction. So that means average the time average pointing vector, the pointing vector will always points along the direction of wave propagation. So that means the direction will be along ax cap. Understood? So this is equal to what? This is equal to half into what is E naught here? What is E naught? So E naught value is 24 pi, right? So E naught value is 24 pi. So that is 24 pi whole square divided by eta naught. Eta naught value is 120 pi. Right, so ax cap. So if you do this, what you are going to get? Tell me. So if you do this, what you are going to get? 24 pi divided by 120 pi, right? So divided by 2. So I think you will get here 7.5398 watt per meter square ax cap. So this is S average here. This is S average we got, right? Is it correct here? Yes. So 7.5398, or you can say simply 7.54. Okay, so this is S average value. Right? Okay. Okay, yeah. So next. Okay. So now see here, if you observe here, S average is independent of what here? S average is some constant value, yes or no? So it is independent of spatial variables, right? So it is independent of spatial variables. So it is some constant value. So whenever if S average is constant value here, you can take it out of the integration or not? Yes or no? It is just like some number. S average, we got some number. Understood? Okay. So you can take that number outside the integration because it is simply a constant. Understood? So this equation 1 here. So therefore I can write the equation 1 in this manner. So that is double integral S average dot dA bar. I can write it as what? So since S average is simply a number I got, yes or no? So it is independent of what? We got it as independent of integration variables, right? So dA bar means you are going to have some spatial variables here. S average is constant, so that is independent of this spatial variables. So that means you can take it out of the integration. So I can write it as what? S average dot what? Dot double integral dA bar. So double integral dA bar is going to give you the total surface area. So that means I can write it as what? S average dot what? Dot A bar, right? Okay. So now we know the magnitude of S average and the direction of S average. Understood? So here we know the magnitude of A bar here, that is the magnitude of the square area, but we don't know the direction of this surface area. So now if you determine the direction of this surface area, then we can represent this A bar. Okay. Okay, yeah. So so therefore power flow through the given surface or through the given surface area, through the given surface area, you can represent it as what? Simply S average dot what? Dot A bar, right? So what are the units here? What are the units of this one? The units are nothing but watts, right? So for this one the units are nothing but watt per meter square, and for this area the units are nothing but meter square. And if you observe, the power flow through a given surface is a scalar quantity or vector quantity? It is nothing but what? The resultant of dot product is nothing but a scalar quantity. So here this is nothing but what? This is a scalar quantity. So these are the things you have to observe here. These are the things you have to observe, right? Okay. Okay. Right. So now our task is to, we have already determined S average. Now our task is to determine A bar. So how you can determine A bar? So A bar is equal to what? Magnitude of A bar, we know this one, and the direction is given by AN cap. So this magnitude also they have given. What they have given? 100 centimeter square, right? So just you have to determine this AN cap. Okay, so if you determine this AN cap, then the problem will be completed. So here how you can determine the AN cap here? Here they have given the equation of the plane as x plus y is equal to 1. The equation of the plane as x plus y is equal to 1, right? Okay. So now you have to determine the direction of this surface here, the direction of this surface, right? Okay, how you can determine the direction of this surface here? See, if you consider in general here, in general equation of a plane is given by ax plus by plus cz is equal to d. So this is the generally the equation of a plane here, right? So that is given by ax plus by plus cz is equal to d. So now the direction of this plane, how to determine the direction of this plane, right? Okay, see, I will tell you a trick here. So one is you can determine the gradient of this one. Okay, so you can determine the, let us say this function is, see see, I can write the same thing. I can write the same thing as it is a function of what? X, Y, Z. A, B, C are constants here. So it is a function of X, Y, Z. So f of X comma Y comma Z. So this D is also some constant, right? A, B, C and D are constants. So I can write f of X comma Y comma Z is equal to some constant. Understood? Okay. Okay here. So f of X comma Y comma Z is equal to constant represents what here? Represents a level surface. A level surface, or you can say equivalued surface here. Equivalued surface. Okay. So in generally we will call this as level surface or constant surface or equivalued surface, right? Okay. Okay. So that means on this surface here, it is going to form a surface. On this surface, at each and every point on this surface, the value of this function will remain same. So that's why it is called as equivalued surface, or we can call it as level surface. So at any point on this surface, right, so the value of the function will remain same. So that is constant. So that's why we call it as level surface or equivalued surface, right? Okay. So for this type of surface here, if you want to determine the direction, so the direction of the surface is given by what? See, this is only for equivalued surface or level surface. Understood? So in this case, the direction of the surface is given by what? Is given by gradient of f divided by what? Magnitude of gradient of f. So this is the method you can follow. If you want, you can follow this one, right? Okay. So that means for the given function, try to determine the gradient and divided by what? Divided by magnitude of gradient. That is going to give you the unit normal. Drawn to that surface. Okay. So which means this is the direction of the given surface. That surface must be what? Level surface or equivalued surface. Only under this case this is valid, right? Okay. So or I will tell you a simple trick here. So there is no need to determine this gradient and all. So you can simply write here, whenever they have given ax plus by plus cz is equal to d. So whenever they have given this type of equation of a plane, then how you can write the unit normal. How you can write unit normal is, so just write down the coefficient of a, write down the coefficient of x here. So the coefficient of x is a, right? So ax cap, and the coefficient of y, so that is b ay cap, and write down the coefficient of z, that is nothing but what? C az cap, divided by what? Divided by, so this is the vector, right? So this vector is nothing but the normal vector to this surface. If you just write down the coefficient of x as x component, coefficient of y as y component, and coefficient of z as z component, this is going to give you the vector that is normal to the surface. Now you want the direction here, so if you want the direction, what you have to do? Take the vector and divide it by its magnitude. So if you divide it with its magnitude, what you are going to get? Square root of a square plus b square plus c square, right? Okay. So if you try to determine the gradient also, you are going to get the same thing, right? So instead of that, just you can directly write here the coefficient of x, coefficient of y, coefficient of z. So this is the vector that is normal to the given surface. You want only direction, which means you have to determine the unit vector. That means take the vector divided by its magnitude. So that is going to give you a n cap, right? Now if you observe here, this equation, the equation of the plane, they have given us what? X plus y is equal to 1. So here, what is the coefficient of x here? The coefficient of x, that is a value, is equal to what? Is equal to 1. The coefficient of y, that is b value is also equal to what? 1, right? And the coefficient of z, here there is no z term. So that means the coefficient of z, c is equal to what? 0. And what is d value? D value is equal to 1. Right? Okay. Okay. So what is the unit normal here? A n cap is equal to what? Is equal to a ax cap, that is 1 into ax cap, plus b ay cap, that is 1 into ay cap. So c value is 0. Okay. So nothing to do with d value, right? So this is this is the value that this function has to satisfy. Okay. Okay. So a n cap is equal to 1 ax cap plus 1 ay cap divided by what? Divided by root 2. Divided by root 2. So this is the direction of the surface. Understood? Okay. Okay, yeah. So if you want how this plane will looks like, we can analyze that one also. So obviously, so here I am drawing here x-axis. Let us say this is x-axis and this is y-axis. So they have given the equation of the plane as x plus y is equal to 1, right? So now see here. Now see, from this equation what I can determine here is I can determine that whenever y equal to 0 here, whenever y equal to 0, what you are getting here, x equal to 1, right? And whenever x is equal to 0, whenever x is equal to 0, y equal to 1, right? So that means this plane is cutting x-axis at x equal to 1. When y equal to 0, x is equal to 1. See, y is equal to 0 means what? Y is equal to 0 means x-axis only, no? Okay, on x-axis where it is intersecting, where this plane is intersecting the x-axis here at x equal to 1, or where it is cutting the x-axis, that is at x equal to 1. Understood? So x equal to 0 means it represents y-axis. Understood? So here we got what? Y equal to 1, which means this plane is going to cut the y-axis at y equal to 1. So that means the plane must look like this here. The plane must look like this. Okay, first I am drawing the line here, right? Okay, so let us say this is what? This is x equal to 1 and this value is what? This value is y equal to 1. So here we are having the restriction on x and y values, yes or no? Okay, so x and y values has to satisfy this condition. So if you draw a plane, on that plane the values of x and y, the values of x and y has to satisfy this equation. So that plane we call it as what? Level surface or level plane. Understood? Okay, here there is no restriction, here there is no restriction, on what? There is no restriction on z, right? So that means z can vary from where to where? Z can vary from minus infinity to plus infinity. So here this is at x equal to 1 it is cutting and at y equal to 1 it is cutting, right? Now if we know that the plane is cutting this x-axis at x equal to 1 and y equal to 1. Now how the plane will look like? So there is no restriction on z here, there is no restriction on z. So that means z-axis is pointing out of the board, right? Z-axis is pointing out of the board. So plus infinity will be out of the board, minus infinity will go into the board. So that means if you place such type of lines here, continuously up to plus infinity on this side and continuously up to minus infinity on the back side, that is going to form what? That is going to form an infinite plane. Yes or no? Okay, so it is going to form an infinite plane, something like this. Okay, so something like this. Okay, I cannot draw the exact diagram here, but you have to understand that if you place such type of lines continuously up to plus infinity and continuously up to minus infinity, so that is going to form what? That is going to form an infinite plane that is cutting the x-axis at x equal to 1 and y-axis at y equal to 1. Understood? So this is what you have to understand, right? Okay, yeah. So now now they are saying that consider only 100 centimeter square, consider only 100 centimeter square. So 100 centimeter square of area, consider only 100 centimeter square of area on this plane and determine the power flow through this square area. That's what they are asking, right? Okay, okay, yeah. What Selvaraj, better to do it on a YZ plane with x-axis pointing outward to visualize how the wave is propagating along x-axis. See here, this is x-axis now. Okay, so this is the plane, the wave is propagating like this, yes or no? The wave is propagating along x direction, so the plane is like this, right? So the plane is like this, right? And the wave is propagating in this direction. Understood? So from here we can say that S average is neither parallel to what? Is neither parallel to the plane nor perpendicular to the plane. So it is going to have what? It is going to have both parallel component as well as tangential component as well as normal component. Only the normal component of the field is going to contribute for the power flow through the surface, right? Okay. See, solving the problem is very simple here. Just we have to do all this analysis. See, for one problem, if we do all the analysis, then whatever the problem that comes in the same model, we can easily answer that, right? Okay. So for the next problem, there is no need to do this much analysis, right? So if we get the same type of problem for the next time, then there is no need to do all the analysis again, right? So for the first problem, we can do all the analysis. We have to learn each and everything. So once we get familiar with that, then we have to apply the concept to the other problems directly, right? Okay. So anyway, so the power flow through a given surface, is equal to what? Is equal to double integral S average dot dA bar. We have seen that the S average, we got it as constant value. So we have written it as what? S average dot what? Dot A bar, right? So S average, what is S average we got here? Just substitute here, now, that's it. So S average, we have already determined 7 point something. Now we got 7 point, where its value, 7.5398 AX cap, 7.5398 AX cap, 7.5398 AX cap dot. So what is this area here? So the magnitude of area is 100 centimeter square, right? So this area is nothing but magnitude of A bar into AN cap. So magnitude of A bar is nothing but 100 centimeter square into AN cap. So what is the unit normal we got? The unit normal we got it as AX cap plus what? AX cap plus AX cap plus AY cap, na? AX cap plus AY cap, right? AX cap plus AY cap by root 2. I think this is the, yes, AX cap plus AY cap by root 2, right? So now if you do this here, what you are going to get? Tell me. So try to do this one here. See here the pointing vector is pointing in AX cap direction, and the surface area is having X component as well as what? Y component. So this AX cap dot AX cap will become 1, and AX cap dot AY cap will become what? Will become 0. Understood? So what you are going to get? 7.5398 into 100 centimeter square, that is 100 into 10 power minus 4 divided by root 2. Okay, so remember you have to give the answer in terms of milliwatts. So here I am writing this. So I am writing this as 10 power minus 1 into 10 power minus 3. Okay, so milliwatts, you have to write in milliwatts. So that's why I am writing 10 power minus 3 separately. So here 10 power minus 1, here 1 0 will get cancelled. So calculate this one here. Calculate this one. So 7.5398 to 10 divided by root 2. Okay, so you are going to get finally 53.31 milliwatts. So this is the answer for this question here. What Kishore Raj, Selvaraj, what you are asking? Sir, if the plane is x plus y equal to 2, will the answer change? No dear. See, S average is not going to change. Yes or no? If the plane is x plus y is equal to 2, so it is nothing to do with S average. Understood? You can determine this one. And a bar is equal to what? Magnitude of a bar to a n cap. Okay, if they have not changed the magnitude, they have given simply 100 centimeters square, then this magnitude is not going to change, right? And what you are saying, x plus y is equal to 2. So if it is x plus y is equal to 2, then a n cap is not going to change. Yes or no? The direction is not going to change. You are going to get what? Same thing, that is ax cap plus ay cap by root 2. So the answer is not going to change. The answer will remain same. If suppose they have given the plane as y plus z is equal to 2 here. In the same problem, if they have given the plane as y plus z is equal to 2. So in this case, what is the power flow through the surface you are going to get? They have changed only the equation of the plane here. They have changed only the equation of the plane. That is, they have given as y plus z is equal to 2. So in this case, what is the power flow through the surface you are going to get? What is the power flow through the surface? Tell me, Selvaraj. If they have changed only the plane equation, that is y plus z is equal to 2. Remaining all data is same, right? So in this case, what is the power flow? Is nothing but 0. Yes or no? Okay. So in this case, the power flow will be 0. Just follow the concept here. Just follow the concepts. That's it, right? So if you follow the concepts, then because the wave is propagating, yes, right? Okay, right. So if you understand the concepts clearly, the basics clearly, okay, so just apply those to the problems. That's it, right? So then there is no way that you are going to do the mistake here. You don't do conceptual mistake. Okay, so in order to there is a chance that you may do mathematical mistakes. Okay, that will be clarified, that will be rectified as you practice here, right? Okay. With this I am winding up the session for today, right? So we have solved different types of problems based on pointing theorem. So if possible, if I find some more new problems, then I will discuss those problems in the tomorrow session. If I don't get some new type of problem here, okay, then I am planning to start transmission lines here. I am planning to start transmission lines. So that is problems on transmission lines. Okay. So problems. I will discuss the problems, and through problems I will try to explain the concepts that is behind these transmission lines, right? Okay. So already in the playlist here, in the EMT playlist, already I have taken some basic lectures, some 2 to 3 lectures, 3 to 4 lectures are present, I think, on transmission lines, right? So basics I have already discussed. Okay. So from tomorrow onwards, I will try to discuss the problems based on transmission lines. So if I find anything about a pointing theorem, if I find any problems in pointing theorem, so then some peculiar problems or some typical problems or some new type of problems, if I find, then I will discuss those problems. So once we complete that, then we are going to start to solve the problems in transmission lines topic, right? Okay. So okay, then with this I am winding up the session for today. So we will meet tomorrow. We'll meet tomorrow at 7:30 p.m. We'll meet tomorrow at 7:30 p.m. right? So our EMT class will be tomorrow at 7:30 p.m. Okay. So okay, then take care. Bye bye.